Today we're going to, the first topic we have is talking about how to get access to and how to get the LiDAR data, the 3DEP data from our website. And we happen to have a recording of a video that that Rob Dollison and Jason Stoker recorded a month or two ago. Well, I guess it was earlier this month, and that goes through it and kind of has a pretty good presentation of that. So we're going to play that video. Hopefully that will work for us here. We just tested it a few minutes ago and finally got it to work. So we'll play that video. It's 15 minutes long, and then we'll have Jason on to answer questions for about 10 minutes or so after that. And then after that, we've got Brittany Gold, who will talk about the WBD in, I believe it's the White Mountains of, is that New Hampshire, Vermont? I've forgotten.
New Hampshire and Maine.
New Hampshire, Maine. Okay, thank you, Brittany. All right, so let's start this video.
Good afternoon. We're here today to talk to you about the National Geospatial Program and how to access the 3DEP Lidar and DEMs to help with your coastal studies. Our goal today is to make sure you know how to access the 3DEP Lidar data and DEMs through our USGS National Map Data Delivery and Services webpage. And we'll also be focusing on the LiDAR, specifically on the LiDAR Explorer application and accessing data without having to download it. This is our National Map Data Delivery homepage. From this site, you can get to our major applications for accessing data, as well as to our map services. So we have things broken up into accessing topo maps, GIS data, and web services. We have over 50 web services, 5 of which are base maps. Up here, you can scroll through our major applications, and the data download application is our primary one for accessing all of our data for vector and raster data. We have a viewer for exploring our data as well through the services, the LiDAR Explorer, which we'll dive into, and we even have a demonstration viewer for working with our elevation services, dynamic elevation services, which you can render on the fly. Jason will be going more into this in the future. So right now I will start off with looking at our national map downloader, give you an idea of what the experience is like here. I'll zoom into Chicago. All right, we will be looking at, for our case, in this case, the source elevation data, our LiDAR data. We can look at where we have LiDAR available. In this case, I can zoom in and select a small area of interest. And search for products. See these, get a listing of the LiDAR tiles and start looking at where those are over my area of interest. We have access to the metadata and other information on the right, but I can also show all footprints or show all thumbnails and get a basic idea of the LiDAR data over this area. From here, I can go look at it to our cart, or get a CSV of a listing of all the files to start downloading. Now I want to show you this similar experience using our LiDAR Explorer, which is optimized more for looking at investigating LiDAR. Here I again have zoomed into Chicago. We can see we have tabs for LiDAR, DEMs, and other products like our IFSAR products in Alaska that you can look at. But I find it's pretty easy right from LiDAR to come in here, show where the LiDAR is available, define my area of interest, and up comes a nice listing of the project, a LiDAR project over this area. I can also get a full listing of the DEMs available, as well as the LiDAR over that area. But one of the key functions here that is different from our generic downloader is I can come in here and you can see this green dot, right, the screen. And this enables me to come in and says, this data has been processed where I can visualize it in the cloud. In this case, we're launching it in a Pottery viewer. And I can zoom in, let's say to Chicago, my areas, and start looking at the actual data before I start to download it. You can even do some processing and working with that data in this viewer. So there's a series of quite a few tools available, in addition to things such as filtering, which you will see down here, filters, and a variety of other things. I'll quickly just show a tool such as a measurement tool that's available here, just to give you a quick idea of how you can explore the data right through the web browser. And you're working with millions of points of LiDAR that you can manipulate and work with even before you decide to download it. So another key component in the LiDAR Explorer is it's still more in the research area, but this is we're starting to have more and more ability to start to process the data in the cloud. And so in this case, it might offer first returns and some processing. It's a more limited capability to experiment with it, but expect this area to grow. And Jason will be taking over the presentation here to talk to us about how to work with the entwined pointile data format up in the cloud. Jason, do you want to take it over?
Sure, thanks, Rob, and hi everybody in the future, and hello to my future self. Hopefully I trimmed my nasty COVID beard between when I'm speaking to you now and when we'll be talking to each other live and in person. So yeah, I'm going to talk about an hour's worth of material in about 7 minutes, so I'm going to move pretty quickly. As Rob mentioned, the focus and the real power that we're seeing now with our LiDAR point cloud data has to do with having it enabled in the cloud, and particularly in the Amazon public data set. So Howard Butler has done a great job getting all of our point cloud data set up in this entwined point tile format that you can see here, which enables us to tap into these data in the cloud and do some processing. So we're moving kind of away from the download first paradigm to being able to have actionable information extraction in the cloud or via other services like on the DEMs, which I'll show in a minute. So if you come to here, you can the registry.opendata USGS LiDAR, you can get to this page. There's some great tutorials on things, and as people build things off this public data set, they're enabling tutorials and links for you to try out as well. So that's really exciting, access to our data in the public data set. Howard has also built this entwined viewer that takes all the projects that we have available in the public data set and has organized them in a way so you can come in and do exactly like what Rob showed just a minute ago. Click on it and you can view in Pottery, for example. So because I don't have a whole lot of time, I'm not going to go into that, but that is available at usgs.entwine.io if you're interested in accessing it this way. The other thing that's really exciting is since this data has been converted into EPT, entwined point tile format, we can apply these scripting tools such as PDAL or Poodle, however you want to say it, to take the data from that public data set bucket and run scripts and processing on it and deliver just what you need. As Rob showed, we have a version available in LiDAR Explorer that enables you to do some small tweaks and small filtering and spit out a Poodle script to JSON set of code that runs through the data and you can apply filters. So if you go to the pdal.io page, you can get to this, and there's a tutorial specifically for reading data from EPT and creating a pipeline using Anaconda. And so I already did that for a small data set here. what I ended up doing is using the tutorial that Howard has on this page, modifying it a bit to create my own thing. So I extracted from this project here in these bounding boxes, read the data, and then just filtered the data that only had classes 1 and 2, and then ran a height above ground filter on it. So it normalizes the data to create that before. So everything is measured from the ground points themselves, and then spit that out on my desktop right now in this script anyway, to this LAZ file. And so in the interest of time, I'm not going to run that. It took about a minute and a half to do. So having a minute and a half just watching processing when you only have 15-minute total is too much. So I ran it here, and so that you can see this is the result. I'm showing it in Global Mapper, but just to give you an idea of how this script worked here. So you can see that it created the height above ground file from that data in the cloud, and then delivered that to me so I could render it here. And you can see it's height above ground because the ground points are all at 0, and the non-ground points are above that. So as Rob mentioned, on that Lidar Explorer page, it'll generate a Poodle pipeline for you that you can then run using Anaconda like this, and then there's a little functionality to run that in the cloud as well. So that's the focus on the point cloud data. I'm now going to quickly talk about the dynamic elevation service we have, which focuses on creating a service that enables you to tap into our elevation data without having to download it. You can find more information at this page here. And so let's see. So what I'm going to highlight is how you get access to this, and how do you put this elevation service into ArcGIS, and I'll even show QGIS real quick. So the link here that is important really doesn't look like much, but if you go up to this WCS link here, you can copy this location, and then if we pull up ArcGIS, add a GIS server. For some reason, for ArcMap, you have to add it as an ArcGIS server. So I'm going to put that here. And here it is. And so it is going to bring in that WCS for us. There we go. And so as you see, all the elevation data that we have available is in this mosaic type data set. So where we have 30-meter data is in here, where we have 1-meter data, it lays on top of that. So as you zoom in closely, the rendering of it will depend on what data sets we have available. I'd always put the highest resolution one on top. So this is showing hillshades, which are nice, but we've been able to render hillshades for a while. The power of the WCS really is the fact that the individual elevation values are there. So what you have to do in order to get to that is, once you load the WCS up, you go to Processing Templates and hit None, and then that will change it to the actual elevation data. So if I were to, I'll just change the color real quick just so we can see. Oh, if I do that, let me do this here so we can see from the current display extent. So that gives you an idea, and you can see that just the values on the scale show you that these are actual elevation data values in meters. So what the power of that is then, if you have that available and you have, you can tap into that, and now you can run tools in Arc on this WCS. And I'm not going to do it because, again, this takes a while to process. But I already ran it. But for example, if you wanted to do curvature, you could run curvature on this WCS and then have it pop up here. And it's tapping into that WCS and you're spitting out the result without having to download all that elevation data yourself. So this is just kind of showing you what curvature would look like for that. So we're hoping you all can take advantage of that. This application. I think it's going to be useful the more people learn about it. So you can do similar things with the WCS and QGIS. I just wanted to show this really quick. If you are interested, you can go to layer, add WCS layer, and then you put that exact same WCS link in from the web page that I showed, and then you can choose the layers that you want to render. In this case, I'm rendering elevation. And as you can see, if we zoom in and out, I'm looking at the elevation data. You can tell that it's actual elevation just based on the numbers that are showing up in the legend. So that's what we wanted to show you in a lightning fashion.
Next, we've got Brittany Gold, who is on the WBD team, and she is going to talk a bit about White Mountains WBD. So Brittany, go ahead and take it away.
Okay, thanks, Al. So hi, everyone. I'm Brittany Gold, and I'm part of the WBD national team. I work with Kim Jones, Lily McNamee, Drew Decker, and Cheryl Boyack, along with many others on national hydrography initiatives and quality control, as well as assisting with local projects. And today I'm going to be talking about a recent project to improve the WBD. With the acquisition of high-resolution elevation data, which that previous talk was a great segue into this, there's been more interest in deriving high-resolution WBD and NHD from this elevation data. Over the past couple of years, I've worked with the Forest Service to update the WBD 12-digit hydrologic units and develop HU 14s and 16s in the White Mountain National Forest in New Hampshire. I'm going to discuss these improvements as well as lessons learned throughout this process. Oh dear, my keyboard is not working to advance the slides. Okay, I'll have to use my mouse. Okay, the White Mountain National Forest covers over 800,000 acres in eastern New Hampshire and western Maine. And the boundary of the White Mountain National Forest is shown here in green. It is one of only 2 national forests in New England, and its landscape is a mix of low-lying hardwood forests and mountainous alpine terrain. Over the past several years, Lidar has been collected in the forest, and 1 and 2 meter DEMs have been developed by mosaicing Lidar tiles of less than 1 meter and resampling to create the 2 meter DEM. This project was an initiative within New Hampshire to update the NHD and WBD in the White Mountain National Forest based on the new Lidar data, and was a cooperative effort among the New Hampshire Geological Survey, Department of Environmental Service, the U.S. Forest Service White Mountain National Forest, and the U.S. Geological Survey Utah Water Science Center. The White Mountain National Forest, seen here with that green outline, intersects 72 12-digit hydrologic units. These units were updated from 1 to 24K topo delineated watersheds to 2 meter LiDAR-derived watersheds using the ArcHydro toolbox. Through this project, 316 14-digit hydrologic units were developed using the 2 meter LiDAR DEM. In addition, I was tasked with creating a catchment for every densified stream segment. Doing so created over 100,000 draft HU16s, which are currently in the review phase. The Forest Service plans to field verify these HU16s as well as the streams within to verify that these should be included in the NHD. The maximum number of HU16s in this area that could be added back into the WBD is around 32,000, since there can be a maximum of 99 HU16s per HU14 due to the hydrologic unit coding for 16-digit watersheds. So the number of HU16s will need to be parsed down prior to going back into the WBD. This is an example of two updated HU12s on the left, outlined in black, with newly created HU14s seen by the red divisions nested inside on the right. The hydrography displayed here is the current NHD, just for visualization purposes, not the draft hydrography. And this illustrates the smaller HU14 subdivisions in the HU12. So this is the same couple of HU12s on the left with those HU14s inside. And then on the right, the orange lines represent the newly created HU16s. And we can see all of the really small near catchment size draft HU16s. So now we'll take a look at the hydrography. The current NHD is in the image on the left here. And on the right is the draft hydrography in the White Mountain National Forest, which is much more densified. The Forest Service plans to field verify these by HU12s and remove any flow line that does not correspond to a stream on the ground. The Forest Service asked for a watershed for every segment of flow line, and they plan to field verify these by HU12, so they're going to verify all of these HU16s by HU12, and they're going to remove any HU16s that either contain an intermittent stream or do not correspond to a stream on the ground. These HU16s will help with forest management, including timber sales and assessment, as well as erosion and other small-scale landscape changes. And this is just a closer look at those HU16s, and so you can really see the level of detail here with a streams of HU16 for every single stream segment, so more of a catchment size data set. So as a byproduct of updating the HU12s, the boundaries at larger scales were also updated, such as the HU4 boundaries seen here. The purple line is the old boundary, and the black line is the LiDAR-derived updated boundary. And we can see a much greater detail in this revised boundary. In addition, using the 2-meter DEM also allows for greater detail, and we can actually see that these stream segments over here flow to the northeast instead of as the WBD was previously delineated, they were flowing down into this Charles River HU12. So this allows for further updating and refinement of the watersheds at all scales. As you can imagine, working in a project like this for the first time, especially developing HU16s and HU14s from scratch, I have quite a few lessons learned that I'd like to pass along for those of you working on a similar project or starting to develop a similar project. The main challenge I faced was working with the draft hydrography. The ArcHydro process that we typically follow includes bringing the hydrography into the DEM. Using hydrography that hasn't been QC'd creates issues in water bodies, double-line streams, culverts, and snapping to outlets. These all have major impacts on catchments that are derived with hydrography in DEMs. This image includes the draft hydrography in blue, HU14s in red, HU12s in black. And this highlights some of the issues with the draft hydrography in the lake and in other areas. So we can see that the draft hydrography just flows straight here instead of following some natural topography. Also through the lake, it's just cutting straight across instead of a QC'd NHD data set would include like an artificial path through here. So one of the main issues I faced was the lack of culverts included in the hydrography and the absence of a culvert data set. Either of these would greatly improve the accuracy and ease of watersheds derived from the elevation and hydrography. Since the draft hydrography did not include many culverts, I created a culvert data set with any major missed culverts that affect the watershed delineations, and I provided that back to New Hampshire so it could be included in the refined hydrography. The state is currently working to create a comprehensive field verified culvert data set, which will be very useful when they create their revised QC'd hydrography. So I'll go through several examples where these missing culverts would have impacted the outlet location, as well as areas that are included in the HU14s and HU12s. In this example and the following examples, the culverts will be circled in purple, the draft hydrography in blue, and the WB boundaries for the HU14s in red and HU12s in black. In this example, the hydrography diverges to the east at the road instead of continuing through these culverts here. And then if we take a look at the DEM, there are 2 visible culverts, and we can make out the channels at the scale here. It's a little trickier up here at the scale. And then also using the NHD, which is in light blue here, that really was able to guide my eyes towards areas with potential issues in the draft hydrography. A similar issue can be seen here where the draft hydrography diverges west at the road. There's a clear channel on either side of the road, and we can even make that out on this imagery at the scale. And there's not a channel heading to the west of this road. And then if we look at the DEM, it's a little tricky to see at the scale, but you definitely don't see a channel heading this direction. And then if we zoom in super tight here, we can see a channel on either side of the road, which would indicate that the hydrography should be routed to the north instead of heading west along the road. And then here's another similar issue with a very clear channel on either side of the DEM, or either side of the road in the DEM, sorry. And then if we take a look with the imagery, you can see a clear channel. The hydrography should be flowing under the road here as indicated by the NHD, and we can even make out the culvert at this scale, looking at this imagery. The absence of culverts included in hydrography and culverts burned into the DEM will not only affect outlet locations, but will also affect catchments that are included in watersheds when running the ArcHydro process. In this image, a large portion of the Johns River unit would have been excluded from the watershed without intervention since there are a couple of missing culverts. We can see that the draft hydrography in the south does not connect to the flow lines in the north in the Johns River unit, while there are 2 visible culverts. And the NHD also indicates that there's flow from the south to the north here instead of due west, like the draft hydrography has. Similar to the previous example, missing culverts in the hydrography impact the size of the unit by excluding or including tributaries that are connected to the main stems by culverts. In this image, the southern portion of the unit would not have been included in the Rattlesnake Mountain Baker River HE14 without the culvert. So we can see all of these flow lines connecting up here and then flowing to the east, whereas there's a culvert right here that would indicate that they should be routed to the north. And if we look closely at that area, we can see this channel here, which we should have routed that hydrography through instead of heading due east. So this is another lesson learned on the importance of QC hydrography as an input for generating accurate watersheds. If HU14s were generated using the ArcHydro process without comparison to the previous hydrologic units, then the entire northern portion of the Upper Ellis River HU14 would have been included with this adjacent Peabody River HU14. So the draft hydrography has the flow lines routed here directly to the east, and so everything north of this purple line would have been lumped with this other HU14. But if we take a look at the DEM, there's actually a valley here that indicates that the flow line should flow to the south here. And if we zoom in really tight there and add some contours, we can see that there's a valley through here and that this draft hydrography crosses a small divide. And the NHG also helps illuminate this. Even in areas that are not heavily urbanized, humans still have an impact on the landscape and on the hydrography. Accurate culvert locations are very important, especially when creating densified hydrography and catchments. Either the inclusion of culverts in the hydrography or at a minimum a culvert data set that could be used to burn into the DEM alongside the hydrography would have improved this process. A culvert data set would also be helpful prior to creating the hydrography. If there are not culverts in the hydrography, there are processes that can be used to help identify them. And Al Ray's discussed subtracting a filled DEM from a raw DEM to help highlight culverts. And this could have been done prior to generating catchments to highlight locations that have been filled and where culverts may be. My colleague developed a tool using this process, and the outputs are seen here in pink. The pink areas highlight potential channels on either side of the road, indicating a possible culvert. And we plan to use this tool to help QC elevation-derived WBD in the future, especially with the upcoming EDH projects. After running the ArcHydro process with the draft hydrography and reviewing and at times manually updating the generated watersheds, there are a few things I would have done differently. I likely would have tried to run the watersheds without burning in the draft hydrography and then intersected the generated watershed boundaries with the draft hydrography to look for potential conflicts that way. I also would have used the existing NHD and draft hydrography to generate culverts and burn those into the DEM. Another way to approach a project like this with draft hydrography would have been to burn in the existing NHD, generate catchments, and then intersect the draft hydrography with the watersheds to look for conflicts that way. With the absence of QC'd hydrography, following these processes would have created purely elevation-derived watersheds without the influence of some of the strange hydrography artifacts, and would have eliminated the need for as much manual intervention and review. Through this process, I was able to provide some level of QC'd hydrography and culverts back to New Hampshire for when they have the capacity to update and field verify the hydrography. This process really solidified the importance of using QC'd hydrography if that's going to be an input in your watershed creation process. QC'd hydrography alleviates issues caused by different flow paths due to anthropogenic influence. It also helps with accurate outlet locations for the watershed, since the WBD outlets are either snapped to NHD flow lines for single line streams or cut perpendicular across NHD area for double line streams. Since the hydrography was not always in the channel of the outlets, I used my best judgment to find the center of the channel and create a WBD boundary that the NHD could be snapped to. Through many iterations with my partners in the Forest Service, we were able to create an accurate and WBD compliant HU14 dataset based on the 2-meter Lidar. I just heard from the New Hampshire Department of Environmental Services that the field-checked Lidar-derived flow lines for one HU12 will undergo geocancellation and will soon be back in the national NHD. This may impact the WBD outlets, which will then in turn be reviewed. NHD and WBD updates are sometimes an iterative process. As a steward or a partner makes changes to one dataset based on better data, then a corresponding change in the other dataset is often necessary. Thank you. Any questions?
Yeah, great. Thanks, Brittany. So folks, if you have questions, I think the chat has been the best way to do that. Go ahead and type your questions there into the chat. So there's a couple of questions in there already, Brittany. Can you see them, or you want me to read them to you?
I can see them. So the first question about why the Forest Service needs the HU16s. I'm not totally sure in the specifics. That was just part of our contract, but one of the understanding was for timber sale assessments. They have a lot of interest in that in those areas, and so they want to assess the downstream implications when there's timber sales. But I can definitely ask my contact in the Forest Service and follow up with you if you'd like, Jane. The second question about the delineation method, I don't know the answer to that. We have a process with Arc Hydro that the WBD team in my office uses, and I am not sure which one we use, but I can look and let you know.
So,
oh, okay. So how many 14? Okay, that she clarified the question. So how did we decide how many 14s the 12 digits were divided into? So the first step we did was to look for the major named streams, brooks, and creeks within the HU12s, and then created them based on that, as well as working with my Forest Service partner to see what really made the most sense with the hydrography in those areas. And through that, we actually ended up breaking out a few different HU12s that were these longer rivers that were lumped in with an existing HU12.
Brittany, this is Sean Vaughn from Minnesota. Can I add to my comment in the chat there about burning streams into the DEMs?
Yes.
I think, first of all, I'm very well versed in the subject matter and been advocating for well over a decade on how best to derive hydrography from LIDAR, and have done a tremendous amount of burning in water courses. We did that in the old days of working with 30-meter DEMs. And I always want to caution folks from a national, when we're reaching out at a national level, that burning in is in, and I'm sure you know this, it's really kind of a band-aid approach, but I understand it buys time, but it leads others to do that. And we really need to be progressive in how we strategize on for working more intuitively with LiDAR derived products, and really thinking more harder about what's lacking in our vector line data, and how can we improve it by working with the DEM instead of burning in old problems into a very new product. And especially when we're talking about 1 meter DMs, and even better with coming from high density LiDAR, I'm really fearful that advocating that at a national scale will lead others to do that. And that's what the comment is about. And I'll stop there. Thank you.
Yeah, I definitely understand that. And the from the WBD perspective, typically we'll burn in the NHD when it's QC'd and checked, and we know that we're burning in good data. And so that helps with our outlet locations, as well as like making sure that we are including what we intend to in the different watersheds. But I definitely understand, especially something like this, where burning in the draft hydrography that wasn't a super high standard creates all kinds of issues. So, and just that's why I think if I were to read on this project, I wouldn't have used the hydrography to begin with.
And Brittany, this is Drew. So you're saying that, right, the corrected data wasn't available anyways for this particular project.
Right.
Yeah, and this Al, I just, I want everybody to understand we're not on a national basis. We're not talking about burning in existing NHD. What we are talking about doing, and what we've been experimenting with, is what we're calling elevation derived hydro. I've seen a couple of references today to LE hydro. That's the old name that we were calling the similar idea, but the idea basically being that we should be using the 1 meter or the high resolution LiDAR data as much as possible. But as Brittany pointed out, there's big problems with just taking that in a raw sense. You need to know, especially where all the culverts are. And so I think existing NHD can be helpful in that regard. And in the work that we've been doing with EDH, we've been using the existing NHD as a guide, and trying to make sure that all those features are represented, but with the understanding that elevation data is really still the key, and that's what should be driving our future, hydrography development, is that high resolution LiDAR data. Let's see. Tracy made a point about sort of the iterative aspect of first editing NHD and then WBD, and then having maybe go back, and forth. And he's wondering about if there's a way to do this together. Do you have any thoughts on that, Brittany?
Right now there really isn't a way to do it together, since the NHD and WBD checkout processes are separate. I don't know if there's discussions about combining them in the future. I think that would be a big model and tool change. So unfortunately, I don't think so. I mean, one thing that could help would be to, if you're a steward or an editor for NHD and WBD, then you could likely avoid the back and forth a little bit between the two checkouts and data sets. But right now, I think, the best thing is to try to handle any possible issues that you might introduce in the other data set before you make the change, or just understand that you'll have to change the other data set and correspond. And there's also the markup tool that can help if you're not an editor in both data sets, and you can submit markups, and that helps to keep both of them current and up to date and clean.
Okay, and yeah, there have been several comments regarding a national culvert database, and I'd love to see it. I'm not sure we're not quite sure how to go about doing that at this point. One way to do it would be as what we're calling addressed data, or to use the older jargon, indexed or event data based on the NHD. But that's still kind of ongoing. We're looking into it, but we're not sure we have the resources to tackle that ourselves. But we're looking at that sort of thing. And yeah, the basic idea that we've got with I think I've talked on this call before, called the National Hydrography Infrastructure, which is sharing a way to share reference data sets or address data sets based off of the NHD, is really kind of what we think might be the best way going forward. And that's where we're not building a single centralized database, but we make it easy for people to share their event data, if you will, in sort of a structure that everybody can share their data through web services, similar to the services that Jason showed earlier, right? Once you have things out in a web service and it's described consistently and everything, then we can do a whole lot of work, pulling those in instead of trying to maintain a centralized database. Gosh, we're running short of time. Brittany, did you see anything more in the comments or questions that you wanted to address?
I think Lily's kind of answered some of the questions going through the comments. One thing that Greg just kind of asked or stated and wanted to confirm was that the hydrography was the LiDAR derived hydrography, but it was a draft version, so it was not QC'd yet, and it has not been field verified. But that is the intention of the Forest Service and the state to go field verify that prior to submitting it back into the NHD. And they've done that for one HU12, but I think that the level of effort might be a few years before they get all of the hydrography there field verified.
All right. I think we may just barely have time to address another question about wide rivers. I think it was Jim's question about wide rivers that might have water surface elevations that varies from reach to reach. Yeah, that's a problem even with this highest resolution LiDAR data. The LiDAR collections may have been done at different times, so you have different water levels, and that's a challenge. And it's not just in rivers, but lakes too. Quite often with reservoirs, maybe the LiDAR was flown when the water was really low, and the water body doesn't look like what we would have in NHD, which would be sort of a normal pool elevation. So that's something we're kind of struggling with right now. Don't have any good answers yet. I want to try and be respectful of everybody's time. So we will go ahead and cut this off here. I'll leave the chat going. I'll leave the meeting going in the chat here for just a couple more minutes. But thanks again for everybody coming, and we will have the recording up on our YouTube channel pretty soon, and we'll see you all next month. Thanks again.